Okay, welcome back to the fixed wing iteration of the robot dynamics lectures. This is the second video segment for the fixed wing lecture, and here we'll be talking about aircraft dynamic modeling. So first thing, why do we want to do this? Kind of the first obvious thing here is that if we have a model, we can then analyze the stability properties of our aircraft. How safe is it? Controllability, do we need to, for example, in our design, increase the size of the actuators to generate bigger moments? Of course, if we have specific missions that we want to accomplish, let's say long-range missions or long-endurance missions, having a model of the aerodynamics will then tell us how much power is required for these things, so either fuel or batteries. And then let's say, for example, we have an actuator failure during a flight. Having this model again would maybe allow us to define some maximum bounds of, if we have like a stuck aileron, what moment it might generate in the worst case. So we can be prepared to compensate this. So kind of similarly then, the autopilot design is something that can benefit from having a model. So either if you're using model-based controls or just trying to test your autopilot in simulation, having this model will be useful, especially since we don't have the ability to fly around in a Vicon room with a fixed wing plane. Every test outside is a bit risky. So if anything is wrong in the code, then it could be catastrophic in the end. So you can normally save a good amount of time by trying to do a bit of parameter tuning and state machine testing, functionality testing in simulation first, and then going outside later. Same kind of situation with pilot training. If the plane is maybe a bit difficult to fly just from its design in manual mode, having this model will be useful for training a pilot in simulation before going out to the real world. So kind of as we mentioned in the last video segments, there's tons of different designs of fixed wing aircraft, and every one of them has a bit of a different dynamic. So an aerobatic plane will be kind of fast and highly maneuverable, where a jetliner is going to be quite slow and stable. But the principles for modeling, it'll be the same. So every plane is going to have some kind of wings and stabilizers. Control surfaces will be utilized for generating moments. So remember, our three specific control surfaces to remember for the lecture are the ailerons for controlling roll, the rudder for controlling yawing moment, and the elevator for pitching moment. Flaps, you can actually see here on the TechPod UAV as well in the picture. They're inboard, so ailerons are outboard, flaps are inboard. Flaps are normally used symmetrically, so to increase lift on takeoff and landing, for example, just to make it a bit slower flight, a bit safer. Spoilers normally used for just generating a bunch of drag, also to slow the plane down. But again, these three are the most important ones that we'll actually use these in our modeling. So then propulsion groups will be around on any kind of plane. And so now down to what we'll do in this lecture, actually, it'll be this plane. So this is the TechPod UAV. It's one we have in the lab. And we'll go through the steps to model this. So first, defining some assumptions and simplifications, going through the fixed wing reference frames, building up forces and moments, and finally getting down to the equations of motion. So if we have some input from our autopilot, for example, this then goes into the actuator dynamics. So there will be normally some kind of delay between your command to this actuator or motor and then when the resulting actuation actually happens. So that's some normally a first order time constant we might use to model these, but they can be measured as well. So you can spool up the motor, let's say on a static test stand, and either measure the force that's acting whenever you give a given input, or measure the RPM, for example, and see what the time constant looks like. Same for the actuator. This can be done maybe with a chirp signal, just to see what that time constant is. So then once we have an actuation, we go into the propulsion group, aerodynamics, they generate forces and moments. Finally, these forces and moments will go into our body dynamics, make our plane fly around. So we get then at the end of the equation of motion, this state dot, and we integrate to repeat the process. So let's get into the assumptions now. We'll define for our body fixed coordinate frame the origin at the center of gravity. We're going to assume that we have a rigid aircraft, also that at least mostly is symmetric. So the y-axis, like the wings, should be the same on either side. This will have some nice simplifications for our inertia matrix later, which you'll see in a couple slides down. We're going to have a constant mass. So we're assuming it's an electric aircraft here, so no fuel loss. Then the motor, we're not going to consider, so you learned about some different gyroscopic effects or hub forces, things like this in the last lecture from Roland on rotorcraft. So we actually will just ignore these. Typically, they can be somewhat neglected for fixed wing aircraft. So now down to aerodynamics. We talked about stall in the last video segment, and we're not going to model this. So you still need to know what stall is, where it will happen, and what kind of the characteristics beyond stall are. But for our model itself, generally planes are trying not to stall. So we're going to only model the part where we're still in that linear nice portion of the lift curve and not in stall. Lift and drag also, of course, exists on the fuselage. We're going to lump this with the rest of the aircraft lift and drag. Side force is something we'll define in a couple slides down, and side slip as well, but these will be neglected. Then no interference effects. So for example, this like turbulent prop wash, we're just going to again ignore. So one of our assumptions was we have a rigid aircraft. Maybe just, I like to show this video to kind of give an example that maybe not all of our assumptions are so airtight. But we'll see that even with something like Atlantic Solar here, who's very kind of flappy with its wings, these modeling assumptions still do pretty well. So just to give a kind of realistic view here of what we're meaning when we say these different assumptions. So now let's get into the kinematics. So we have our body fixed frame with the CG as the origin, as we mentioned before, and this is offset somewhere from an inertial frame. And generally then, so actually, sorry, this is always for a fixed wing, we will have this northeast down coordinate system. So this is different from the robotic frame, so the E and U, I believe. So if you were still using cardinal coordinates here. So just remember, this is it's an aerospace convention, northeast down. So then that x-axis is the northing, y-axis the easting, and z-axis down. So then for the plane itself, you can remember this nicely by saying that x is always out the nose, y is out the right wing, and then z you can complete with the right-hand rule. We also do, for the inertial frame here, a flat Earth assumption. So this is a local inertial frame. So we're not using lat long coordinates. We're assuming we have some point, yeah, where do you define this origin? We're assuming we have some point, either, for example, the UTM coordinates or a home position or start position. This is actually the more typical way for small drones. We boot up the plane, and once the estimator is happy, home position set, and this is now our home inertial local coordinate, from which we then define this position vector to our center of gravity. So again, body fixed frame, x out the nose, y out the right wing, z down with the right hand rule. And origin located center of gravity. So now looking bit more on the body axis side of things. So we are flying with some airspeed. So here what we'll do is represent this body velocity with a subscript A. And when you see that A, it means it's the air mass relative speed. So air mass relative speed. What does that mean? Airspeed, it means the speed at which we're flying through the air mass. So this is important as a distinction because in a few slides later, you're going to see a inertially defined wind. And this wind is basically, we're assuming that that air mass itself is moving, and that's what the effective wind is. So that's why we need to really distinguish A, for airspeed, this is relative to the air mass in which we're flying. So V capital is just the magnitude of our airspeed, and we'll assume it's always positive. Then we get body rates. So maybe just to point out, like the UVW here for the body velocities, this is just a standard aerospace convention for the nomenclature. So just that's why I wanted to show you here, because this is actually any aero textbook you pick up. Very often they will use these particular symbols for body velocities, and then again here these particular P, Q, and R for roll rate, pitch rate, and yaw rate. So these are again aero conventions. So then maybe some new stuff. So this is where fixed wings are then a bit different from other flying platforms. So we have another axis. Again, this is an aerospace convention. It's called the wind axis. So this we rotate through the angle of attack and then over on the side slip. So I mentioned we'd clarify side slip. So side slip means we have incoming airflow on some side of the aircraft. So this would, in principle, generate some kind of side force also on the aircraft along the y-axis. So airflow angles, again, this is the angle of attack, so we can construct it from the body velocities. Side slip we can construct also from body velocity and or side velocity and the magnitude. Again, this lecture will normally assume that side slip is 0, but just so that you know where it is. So the wind frame is defined opposite to the free stream velocity. So this is yet another aero term that I think you should know. So down here, this V infinity, if you ever see this in literature somewhere, this is the free stream velocity. And so the difference here is that this free stream velocity, it's actually the same as the airspeed, but it's pointing in the opposite direction. So this is basically, so possible point of confusion. So the wind axis itself has no relation to the external wind inertial sense, so it's not the movement of the air mass. It is basically our movement through the air mass. The wind frame, yeah, again, air mass relative velocity. But the naming convention, that's what I wanted to get to, is that the reason why this wind axis exists, it's called wind, is because of aerodynamicists who were referring to the incoming flow. And that's the same with that free stream velocity. The free stream pointing in the other direction is, again, kind of aerodynamicists like operating in wind tunnels saying, oh, the flow is coming towards us. So just so that you know, there's the different conventions. We'll talk about airspeed as our air mass relative motion, through the air mass, so pointing out from our center of gravity, whereas the free stream, V infinity, is going back the opposite direction. So I won't go too much into detail for Euler angles or coordinate transforms, because I think Roland did a quite nice job in his video segments, so you can maybe go back to refer to those. The Euler angles we use are the same, Tate-Bryan angles, so it'll be the same kind of development. So that's how we go between orientation of the inertial frame and the body frame. So these plots you'll find familiar if you went through Roland's lecture. So again, I won't go into the details. I think Roland did a good job. But you have to rotate through each axis, yaw, pitch, roll. That's specific to Tate-Bryan here. And these are the Euler convention that we use for fixed wing. So maybe then a brief note on angular rates. Just to remember, the time variation of Tate-Bryan angles is not equal to the body angular rates. So there is a transform here that's necessary. So this L matrix here from Euler rate to body rate, angular rates, looks like this. So it's a function of your pitch and roll. The other thing about this matrix is that there is a singularity at plus or minus pitch is equal to 90 degrees. So some implications of this, so it's called gimbal lock commonly, and also we then know that we can't directly use the transpose as the inverse like we did with the other rotations for the Euler angles. So this one needs to be the proper inverse, and yeah, it's not orthonormal. So then moving on, there's another coordinate frame that actually is somewhat useful for higher level modeling tasks. So here we're looking at kind of a side view of the plane. So we'll call it the longitudinal inertial frame. And these are polar coordinates. So here in E, this dotted line is the horizon. So this is just horizontal inertial horizon. It doesn't really matter which direction you're facing. It's just the horizon in general. So first notation here is the flight path angle. So flight path angle is also kind of synonymous with the glide slope. So if it's going the other direction, so we're not going up, but we're going down and we have no throttle. This is if someone tells you, oh, I have a glide slope of, or a glide angle of 5 degrees, they're actually referring to -5 degrees flight path angle. So this one is from the horizon to the airspeed vector. So that's really important to remember, that flight path angle goes to the airspeed vector, not to the body axis. So pitch angle will go up to the body axis here, and then angle of attack when we're only looking here, so assuming roll is and slip is 0, angle of attack is in the difference between them. So from airspeed vector to body axis is our angle of attack. So that's our angle with respect to the incoming flow. Then we get these 3 longitudinal angles. So pitch again, horizon to body axis, roll angle then down here. So again, this depiction is assuming pitch is equal to 0. So then we have from horizon to the wing a positive pitch looking like this. And then again, we can transform between body defined UVW airspeed components to the inertially defined airspeed components to show this here in the inertial frame. So now if we look down at the top view, still in polar coordinates here, we'll look at the lateral directional inertial frame. So here's again our inertially defined airspeed vector, slipped a bit from the x body axis. Another angle that's quite often used is the heading angle. So this is from the north axis to, so inertial defined north axis to the airspeed vector, that's heading. So this should be distinguished from yaw angle. So these are often confused. They have specific meanings. So heading is from north to airspeed vector. Yaw, so here, this one, is from north to x body axis. So this is to our body axis. Then this still doesn't consider wind. So now finally we're going to actually talk about like wind when we talk about a moving air mass. So if we add a constant steady horizontal wind, so we're assuming there's no vertical component here, now we can actually sum these two vectors. So the reason we can do this is that we're assuming it's steady and it's constant. So steady meaning there's no transient effects, no forces acting on the plane. It's just a steady velocity increment to our ground speed. And then our ground speed shown here. So airspeed vector plus wind speed vector. So the actual velocity of that air mass that we're flying in equals then the final ground velocity. And this is what your GPS is going to be measuring, for example, is the ground velocity. But this is then again why it's important to really distinguish these two, because air velocity is not the same as what the GPS actually gives you. You have to somehow estimate or consider the wind. So then another angle that's useful, so course. If anyone tells you the word, what is your course? Course is just our angle between north and ground velocity. Yes, so ground velocity there. So the magnitude then, it's called ground speed often. Wind velocity Yes, and so another nice thing here is that since, again, we have this constant steady wind assumption, only the position dynamics are affected by the wind. So we don't need to worry about, gusts on one side of the wing or something like this, and the kind of weird effects that can happen then. So now summing up with all the polar coordinates, basically then this is our position dynamics. So how does the position change? We have just our airspeed, flight path angle, heading angle, and then we add on those wind components after the fact here. And then we get to that ground velocity and how our aircraft is finally moving. So with kinematics described and all of these mini aerospace specific notations and definitions, we can move on to the dynamics. So forces and moments. So the first thing, non-aerodynamic forces. So we of course have gravity acting at the CG. All of these forces will be summed about the CG. So then we have thrust. Note that thrust can be offset somewhat from the body axis. It could have some inclination angle here. So we put epsilon for this inclination angle. It's very common for a couple degrees for the motor to be propped up. So here that's just how it's denoted, epsilon. We will assume though that it's not sideways mounted in some way. That's another thing that can commonly happen on small planes is the designer might mount the motor a little bit to the left or to the right to compensate for those gyroscopic effects, thrust torques that we're ignoring in this lecture. So now we move on to aerodynamic forces. So of course we need to be flying at some airspeed to get any kind of aerodynamic force. So the first one, again, remember, perpendicular to the airflow. So we have lift. And this is then our 3D version of that equation. And this is a lumped lift equation summed at the CG. So this is considering our whole wing, fully integrated, our fuselage lift, tail lift, everything lift, all summed into one about the CG. So surface area here is, I'll get to in a second actually, but then this lift coefficient again is a 3D version, so capital L. So this lift coefficient is for the whole plane, aircraft lift coefficient. Similarly, we have the drag equation, so parallel to the airflow. Again, perpendicular and parallel, please remember. And then side force, I mentioned we define a bit earlier. So assume this is 0 for the lecture. We won't use this. We're saying that our slip is 0, and so this side slip should be 0. So I told you I'd come back to the surface area, so this S here. So if we look at our top view of a wing over here, so the surface area that we're talking about is also from the top view called the planform area. That's another word for it. So this is really top view area. It's not considering the curvature of the wing. So this is the common term used to normalize this whole, to normalize the lift and drag coefficients. So whenever you see equations like this for a different aircraft, you know this S is responding or corresponding to the whole planform area. So now to the moments. So out the x-axis or x-body axis, we have our rolling moment, pitching moment out the y, yawing moment out the z. And here again, some definitions. So this B is span. This is basically just the length from tip to tip of the wings. This is used for normalization of these coefficients for the rolling and yawing moments. So these are lateral directional moments. So they use span. It's just aero convention. Then there's the chord. So at any point in the wing, it could be different. So here we take the mean geometric chord, which you can calculate by kind of drawing these lines and taking the center point. And this mean geometric chord then is used for the longitudinal pitching moment normalization of the coefficient. So there's some more details on these wing geometry in the backup slides if you're interested, but these are the main things you need to know. So now, finally, how do we actually model these if we don't have, for example, CFD or some kind of wind tunnel test? how then from flight data would we build up these lift and drag coefficients? So the most typical way is to use what's called the component buildup approach. So what that literally means is we're building up from various components. So it's just a Taylor expansion. So here you can see first order Taylor expansion. So we're just saying linear terms only. We got like elevator deflection here acting against some lift per elevator, just in a linear approach. So these are all individual coefficients. So angle of attack is a linear term, pitch rate is a linear term. Second order could also be used. So depending on how weird the aerodynamic might be, we might have a squared term for alpha. Maybe we have some coupled terms, so cross terms here like alpha and elevator, so angle of attack and elevator. And then beyond this, just note that all this nomenclature here with the lift coefficient and a subscript. The subscript just refers to what we're taking a differential, or what with respect to which state we're taking the differential of this coefficient. So that's nomenclature. So other model structures actually could be used and actually should be used sometimes, depending on the aircraft design. But for us, we're really going to stick just to this simple kind of component buildup approach. It generalizes quite well in practice. Okay, so now that we know what our lift and drag and thrusting forces are, we can build up the forces. Basically, we sum everything that we have in body frame. So gravity is also acting in the body frame, so we need that force. So we can translate that, transform that with the transformation matrix. Then we have thrust with our inclination, and then rotating the lift and drag through angle of attack, since we assume slip is 0. And then we have a side force here if there were any side force not from side slip. Again, we're really assuming it's a 0 in the lecture. Then, yes, so in the end, we get these full equations. So then if we sum up the moments, again, here in the lecture, we're going to assume that these moments from the thrust or from the propulsion are negligible or 0. So this is just really here for completion, but otherwise the moments can kind of just be directly summed. And now finally to the equations of motion. So for the translational equations of motion, so I won't go through the derivation here. I think it's already been done multiple times in the previous robot dynamics lectures. So here you have kind of the end result. Again, remember, we're only looking air mass relative here with the body axis time rate of the velocities. So then we have our sum of the forces from the previous slide, and then this Coriolis term here for the position dynamics, same as we saw in the polar coordinate slide. Now we get down to rotation. So we have the angular rate time derivative. And here's where our mass moment of inertia comes back. Or inertia matrix. So this is what this I is in the body frame. So also then our sum of moments. So something to note here, I mentioned I'd bring this back up. So since we assumed symmetry of our y-axis, all of these products of inertia here that have a y in their formulation can be 0, because the mass distribution on either side of the y-axis was the same. So then the integral ends up becoming 0 for all these terms. So then we can get rid of these. Now we still have the x, y, z, so the diagonal here that we need to either identify or measure. Also, this xz product of inertia is actually not gone. So it is typically small for a regular fixed wing aircraft because their z axis mass distribution is typically not terribly different on either side of the x-axis or z-axis, and the x similarly, but there will be some small number here, so this has to be calculated. So then finally we get our, again, same Euler rates for rotation. Small side note here on those mass moments of inertia. How do we get them? So we do what's called a swing test. At least this is one approach to get the mass moments of inertia. So this is something you can set up as a pendulum, and then the way it's modeled is that on board we have our IMU where we can kind of measure the frequency of these oscillations, and then if you model the whole thing as a compound pendulum, that's what the swing test method does. You can back out then the moment of inertia in each of these axes. So there at the bottom left, XX at the top left, YY, and at the bottom right, ZZ. So then what does the XZ look like? At least we attempted to do it this way, but XZ is actually quite hard to do the swing test for. The results are normally quite different every time, or not so repeatable every time you do it. In principle, you should be able to somehow get an XZ from this type of swing test. So now we've completed the second video lecture. So on modeling of fixed wing aircraft, the next lecture will dive into the control. So see you on that one.